Hey everyone, and welcome. So today, we're going to peel back the curtain. We're going to look past all the code and the algorithms and get right down to the metal, the incredible, mind-bending physical hardware that actually makes artificial intelligence work. We're talking silicon, we're talking light, and we're talking about a scale that is just staggering.
Let's just start with a number to get our heads around this. 12 trillion words. That's a rough estimate of how many words Google's AI systems process every single day. I mean, trying to even comprehend that amount of information is almost impossible, and it just perfectly frames the colossal demand that modern AI places on our hardware.
And yeah, that brings us to the big question, right? When you type a prompt into an LLM, what is physically happening? What gears are turning? What switches are flipping? What connections are firing up to bring you that answer in seconds? We're about to go from this abstract world of data into the very concrete, very real world of hardware.
So to get to the bottom of this, here's how we're going to break it down. First, we'll look at AI's just insane appetite for power. Then, we'll diagnose the two huge bottlenecks that are holding everything back. After that, we'll dive into how engineers are literally reinventing the microchip, connecting them with light itself, and finally, what the blueprint for the computer of the future really looks like.
Okay, so before we can even talk about the solutions, we first have to really truly appreciate the scale of the problem we're facing. Modern AI, it doesn't just need a lot of computing power. It needs a frankly unimaginable amount, and it needs the physical infrastructure to back it all up.
And you can see this happening right now. Just look at the headlines. OpenAI is reportedly talking about a $500 billion data center that would need 5 gigawatts of power. That's enough to run a small country. And of course, Meta's not sitting still. They're planning their own 5-gigawatt facility. But here's the really fascinating twist. For these mega projects, the main challenge isn't just cramming in more processors anymore. The real problem, the true bottleneck, has become just moving the data around.
And this whole data problem? Well, it has two main villains in our story. We call them the memory wall and the copper wall. These are the hard, physical limits that are slowing down AI's progress. And let me tell you, breaking through them is the #1 obsession for the entire tech industry right now.
So, first up, let's talk about the memory wall. The best way to think about it is like this. Imagine you've got the fastest, most brilliant chef in the world, but their kitchen assistants are super slow and can only bring them one ingredient every 10 seconds. What happens? Well, that world-class chef spends most of their time just standing around waiting. And that's exactly what's happening to our most powerful AI chips. It's kind of crazy, but studies show that these GPUs can spend over half their time, 50%, just sitting idle, waiting for data to show up from memory.
And this really gets to the heart of why GPUs are both the heroes and kind of the victims here. See, a GPU is all about parallel processing. It dedicates its precious silicon space to thousands of simple little cores that are perfect for the kind of math AI needs. But to make room for all those cores, they have to sacrifice the big smart caches that a CPU has to keep data nearby. And that very design choice makes them incredibly powerful, but also incredibly vulnerable to that memory wall.
And then there's villain number 2, the copper wall. For decades, we've connected everything on a chip with tiny copper wires. But we're hitting a fundamental limit of physics. When you try to push more and more electrical data through those tiny wires, faster and faster, the signal starts to break down. It generates a ton of heat, and it creates interference. We have basically squeezed every last drop of performance out of copper, and it's just not enough anymore.
So, okay, you've got these two massive walls blocking the path forward. What do? Well, the first battle is being fought right on the processor itself. The whole goal is to make the silicon do way more work with the data it already has, so it doesn't have to keep going back to memory over and over again.
You can literally see this strategy playing out if you look at the evolution of AI chips over the last few years. There has been this relentless march towards what's called lower precision math. It's a simple idea, really. You don't need a super precise number with 10 decimal places to figure out if that's a cat or a dog in a picture. A much shorter, simpler number works just fine. So by using these 16-bit, 8-bit, and now even 4-bit numbers, you're moving and storing way less data, and that is a huge, huge win.
And that's the whole magic trick right there. By using these less precise 4-bit numbers, what they call FP4, the newest chips can get these massive performance boosts, especially for things like model inference. You're basically trading a tiny, insignificant amount of numerical accuracy for a giant leap in speed and efficiency. And in the world of AI, that's a trade you make every single time.
And this isn't just one company's story. If you look across the whole competitive landscape, everyone is having to make these tough choices to meet the demands of AI.
You've got NVIDIA's Blackwell going all in on AI and path tracing. You have AMD with RDNA 4 really focusing on core graphics performance. And then Intel's Battlemage is carving out a spot in the mid-range. Each one is a slightly different answer to the exact same problem. How do you get more work done for every watt of power and every bit of data?
But look, smarter chips are only part of the solution. To really get to the next level, we also have to completely change how data moves between those chips. And then we need way more intelligent software to manage that whole incredibly complex system.
So, to smash through that copper wall, the entire industry is turning to something called silicon photonics, basically using light instead of electricity to move data, and it is a total game changer. Light pulses don't generate the same heat, they don't interfere with each other, they don't lose signal strength over distance. It's like replacing a permanently gridlocked highway with a network of teleporters for your data. And the impact is just wow, 8 terabits per second. That is the kind of bandwidth that companies like IR Labs can now get from a single tiny optical chiplet. That's the kind of massive leap in data transfer speed you get when you switch from pushing electrons around to sending photons. Okay, so you have these unbelievably fast chips and connections made of pure light. Problem solved, right? Not even close, because all this amazing hardware creates its own kind of chaos. You now need a really sophisticated software layer to act as the conductor for this massive high-tech orchestra, making sure every single component is playing its part perfectly.
Because without that smart management, it's shocking how inefficient things are. Those super expensive GPUs, they often just sit there, idle, with utilization rates as low as 15 or 20%. It's a huge waste. And that's where orchestration software comes in. Take NVIDIA's Run AI, for example. It's like an expert air traffic controller for the data center. It pools all the GPU resources and dynamically assigns them to different jobs, pushing that utilization rate way up to 80% or more. That's up to a 5 times improvement in pure efficiency.
All right, so now let's put all these pieces together. We've got smarter chips, we've got light-speed connections, and we've got intelligent software. Let's see what the new blueprint for computing in the age of AI actually looks like. It all starts at the most fundamental level, the transistor. Those microscopic little switches are the building blocks of everything. The old design, called FinFET, is hitting a hard physical wall. So the successor is something called Gate-All-Around, or GAF-FET. It's a really clever redesign. By completely wrapping the part of the transistor that controls the electricity, it basically plugs all the tiny energy leaks that waste power and create heat. The result? A huge boost in either performance or power efficiency as we move down to the 2-nanometer scale. And this new blueprint, it looks totally different from the computers we're used to. We're moving away from these big, single, monolithic chips. Instead, the future is disaggregated chiplets, where each little piece is specialized for one task. All these chiplets are then connected by a super-fast fabric of light. And this whole massive pool of resources is managed by that intelligent software, making the entire data center act like one giant, powerful, cohesive computer. So if there's one thing you take away from all this, it should be this. The computer of the future isn't a box that sits on your desk, or even a server rack. It is the building. It's a massive, building-sized, light-speed fabric of computation, constantly reconfiguring itself to solve the world's most complex problems.